cache is the highest level in memory hierarchy right next to the processor so that we can access to this cache a faster way. And it's really fast. Typically the one cycle access time ideally supplies most of the data to the processor. Ideally, but it's not possible. Usually holds the most recently accessed data. So anything we get from the main memory, before we process, we're going to store that in the cache because we might need to use that data again in the future. So to design the cache, these are the questions that we need to think about. What data is held in the cache? Before we getting into main memory, I want to see whether I have that information in the cache or not. That's the one. Second, and if there is the data in the cache, how we find it, that's the second. And then how we replaced, okay, that's the third one. So we need to consider this temporal locality and spatial locality when you design the cache. And these are the terms that we saw last time as well. I mean, I don't have to worry too much about it. We're going to go through all of those. For our class, we're going to look at the direct map, one-way set associative, two-way set associative, three-way set associative, and fully associative cache design. So let's do this. Show the addresses of memory words between 0 and 31 using direct map cache with the size of 8 blocks. So I'll show you what is the direct map. And another keyword, memory words. In our definition, how many bits in word? 32 bits. How many bytes? 4 bytes. Okay, so now we have 8 blocks. So these are the 8 blocks of the cache. We want to name these 8 different blocks using binary numbers. How many bits do we need to name these 8 different blocks? 3, because we're going to go from 0, 0, 0 all the way down to 1, 1, 1. Now we have a main memory and there are 32 different blocks there, and if I need to name them, I need to go from 0, 0, 0, 0, 0 all the way down to 1, 1, 1, 1, 1. So we need the 5 bits. Since we have much smaller cache than main memory, that's always true. Somehow we need to have some logic which one is going to store in where, right? What do you think? What's the easiest way? Since we are using binary numbers, and this is the memory address in words, and if we can use lower 3 bits, just like this, lower 3 bits, as some sort of indication to location of the cache, that's one way. So that's the typical way, and that is the direct map. So I'm going to use lower 3 bit. If the lower 3 bit is 0, 0, 0, I'm going to store into cache 0, 0, 0. And this cache address, we also call it as an index or set, S-E-T. Our textbook uses set, and then some other textbook, typically we use index, so I'm going to use index. The memory address 0 is going to go here, and when we have 1, 2, 4, 8, 16, and 16, lower 3 bits of the 16 also 0, and lower 3 bit for 8 is also 0, 0, 0. So this guy is going to go here, this guy is going to go here, this guy is going to go here. And then 0, 0, 0, 0, 1 is going to be here because the index value is 0, 0, 1. Make sense? So that's the direct map. And since we have 8 blocks, we're going to use mod 8. Since we are using binary number, log 2 of total 8 blocks, 3, that is the 3 bits. That's typically how we calculate that, but by now we know how many bits is required if we know total number of blocks, right? And then address of, for example, 22 mod 8, which is 6, or we're going to just use the lower 3 bits for the location of the cache, kind of showing the mathematical way to show that where each main memory address map into certain number of blocks in the cache. Then we have a 0, 8, as I said, 16, 24. All of these map into 0, 0, 0. And let's do one more example. 6 and the 14, 22, 30. Those are the ones map into 1, 1, 0. So whenever we have main memory address, after you put it into binary number, we use lower bits to identify index value of the cache that where we want to store that. And you can do the rest. So now we have the memory address is in ARM. This time I said ARM. And for our process, now the memory address goes up something like this. It's different from the previous example. In the previous example, memory addresses were in words, but this one is a 0, 4, 8, 12, 16. Why? Why? Exactly. It's a byte address. When you convert from C to ARM, okay, whenever it's in the C code, memory access to the array 2, we need to multiply that by 4. And in actual ARM, we have to use 8, right? Because the memory address is a byte address. So this is the byte 0 right there. Is byte 0, byte 1, byte 2, byte 3. Okay? And then byte 4, byte 5, byte 6, byte 7, and 8, and so on. Now this time, we cannot use lower 2-bit. They are all zeros. So we cannot use lower bits for the index this time. So in this case, we have to use, if we have 4 blocks, if you have 4 blocks, we need to have 2-bit binary numbers, and then we're going to set aside lower 2-bit, because they're all 0, we cannot use that. And then after lower 2-bit, there's extra 2 bits. That's something we can use as an index. In here, 0, 0, 0, 0, 0, 0 is going to be in the 0, 0, 1, 0, 0, 0, 0 is going to be 0, 0, 1, 1, 0, 0 is going to be here. So in here, the lower 2 bits, we're going to call it offset. This lower 2-bit is the offset, and actually where within this byte addressing. We'll see this again a little bit later. And in this middle 2 bits, we said that is index. Now, this guy is 0, 0, 0, 0, 0, 0. It's gonna put it in, we're gonna put it in here, right? And also, if you have 0, 1, 0, 0, 0, 0, okay, if you need to bring this guy, and then I have to replace all the value from here. Now, we have this one, and this one. Really, I want to use the content of cache, but I don't know which one is really in the cache, right? Because 110000 is also in the location of this, the cache location, and 010000 is also, it's going to be on this location. We don't know which one is really which, so we need extra values. We call it the tag. So the rest of the bits is the tag. So I know by looking at the tag, it's a 0, 0 in here, then this is the only one. Okay? So I know, hey, this is what I want, or hey, this is not what I want. Actually, I want 010000. Then I need to go down in the main memory, bring this guy, and replace the older value of 000000. So tag is also play the important role in the cache design. So that's the tag. So when we look at all of these, we're gonna have the red one is a tag this time, black one is the index or set, and lower 2 bits is offset of the data. So in the example, in the book, say 0x00000014, where are we going to store into the cache? So now we need to put that into binary number, and lower 2-bit is going to be what? Offset, And then since we have 8 blocks, next 3 bits is going to be the location of the cache, which is 101 and here. And then the rest, okay, all the rest is going to be our tag values. And name other addresses. So we have 1434, 5474, all the way down to F4. Anything the lower hex value is 4, we're going to store into the same location of the cache, which is 101. Make sense? Yeah. Question is, offset is always 2-bit? Not really. We'll see later, because the cache, where sometimes we're going to have larger cache, so it's not going to be cache size is not always 32-bit. If the cache size is always 32-bit, then yeah, byte offset has to be always 2. But if the cache size, the block size is the 2 word, then offset is going to be different. Okay? We'll look at the example as well. Find the number of set index and the tag bits for the direct map cache with the 1024 blocks and 1 word block size. And the address is the 32 bits. The memory address format is this. For our architecture, is a 32-bit memory address as a 32-bit as well. The lowest bit is the offset. In the middle index, the rest is the tag. So we have 1024 blocks. It's a good number, right? If we have a 1024 blocks, series of blocks, how many bits do we need to name all of those 1024? How many bits? 10. 2 to the power of 10, kilo. 1024 blocks, that means 2 to the x equals to 1024. X is 10, 2 to the 10, 1024. That's our kilo. How many bits of the index? 10. How many bits of offset? 2. Why? Why 2? 32 bits. Yeah, but why offset is 2? 1 word, which means 4 byte. We need to access each byte. LDRB, STRB. So storing and loading in byte-wise in ARM architecture. Therefore, offset has to be 2, and index bits should be 10, offset should be 2. So those are the ones that you need to figure it out first. And then tag is 32 minus this guy. Therefore, it's a 20 bits. I don't know what, I just copy and paste from the book, but I have no idea what they're saying. So don't even bother with the bottom one. So you just want to go with that. So now, here's the thing. I give you some description, and then I'm going to ask you to find the total size of the cache. Okay? And the total size of the cache, we need to calculate using this formula. So that's something you need to write on your cheat sheet for the second exam. 2 to the power of n times the block size plus tag size plus valid bit to calculate 2 to the n. Okay? So what we need to do, we need to have a cache size divided by the block size. Okay? From there, we need to figure it out what's the n value, and that n is the total number of bits for index. So this will give us total number of blocks. Cache size divided by block size is the total number of blocks, right? If we know total number of blocks, 2 to the power of x equals the total number of blocks, just like what we did in the previous example. So that will give us n value, and that is the total number of bits for index or sets. And then we need to figure it out, the tag size. The tag size equals to 32. For our architecture, memory address always 32. So 32 minus n, we figured it out, n, plus m plus 2. And the m, we're going to look at the block size as the words. And then 2 to the power of m words, this m value will give us in here. What about this 2? Why we have 2? This is from byte addressing. So back to answer question. If we have 1 word block, this m value is going to be 0, right? It's 1 word. Therefore, this guy is 0, so offset is only 2-bit. However, we could have 2 words block. If 2 words block, that means 2 to the power of 1. M value is going to be 1. 1 plus 2, that's the 3 bits for the offset. So this M plus 2 will give us the total number of bits for offset. Make sense? Take a note on that. M plus 2 is actual number of bits for the offset. And these 2 is always true because in our architecture, one word, we have 4 bytes. Therefore, we need to have, by default, 2 bits for the offset. And if you have a larger cache, one word is a 2-bit offset, 2 words, 3-bit offset, 4 words, 4-bit offset, and so on. How we find the total number of offset? By looking at the block size in word so that we can figure it out. 2 to the power of M, this M value will give us additional offset for that larger cache. And then the valid bit is always 1, okay, 1 bit. Either we have cache or no. We have in that very specific location, if the valid bit is 1, then there is cache. If its valid bit is 0, we don't have to even bother to look into one, right? Because the cache is empty on that block. So when you calculate this guy, valid bit is a bit, right? The unit is bit. So all of this, make sure you have to change this text size, and especially for block size, you have to change that into bit. Otherwise, you cannot add bit with the byte or bit with the words. In the problem statement, you're going to get how many bytes, how many words, all mixed in a unit. So you have to change everything into bit and plug it in here. And the 2 to the n times that is the actual cache size. Finding this cache size, 2 to the n is the vertical weight, right? 2 to the n. Let's say we have 10 bits of index, then 2 to the 10, which is 1024, which means there are 1024 blocks. That's the height of the box times width of the box. So the width of the cache is the valid bit plus tag plus total block. So basically this calculation is you're just multiplying width and times height of the cache. Let's do this. Copy this down. Size of direct map cache with 8 words with a block size of 4 byte in an ARM processor. So we need this. Let's figure it out. The size of this cache. The first thing, 2 to the n equals to cache size over block size. What's the cache size? 8 words, that's the cache size. And the block size, 4 byte. So we have 2 to the n equals to cache size is what? 8 words. And then the block size is the 4 byte. So now 8 times 1 word is going to be 4 byte over 4 byte. It's going to go away. Equals 8, 2 to the power of 3. So n equals to 3. The block size, we said, equals 4 byte, which is 1 word, which is 2 to the power of 0 word. So from here, m equals to 0. The text size equals 32 minus n plus m plus 2. So that is 27. So now the block size, we have a 32 bits, text size 27 bits, and then valid bit is 1. So that is the total size of cache, 8 by 60. Yeah, everything has to be in bits. If I ask you to find byte, I mean simply you can say 60 byte, right? So this is the inside cache. We have 1 bit for valid bit and then X number of the tag bit, X number of the data. So as a process, I want to get into main memory, memory location 7. The first thing I want to do is see whether I have that memory 7 information in the cache or not, right? So I'm going to look at this valid bit first in the 7. If valid bit is 0, done, because there's nothing in here. So I'm going to just go down main memory, bring that into cache, and I'm going to use it. However, if I look at the 7 and valid bit is 1, that means there's a something in that cache. So next thing I want to check is the tag value. See whether that's the right one that I need. The one that I want, okay, versus the tag value in the cache. If they are the same, that's the hit. If it's not the same, I need to go down, bring it again, and that's the miss. So valid bit is always 1 bit. See whether we have something in the cache is 1. If we don't have anything in cache in the 0. So initial value for this valid bit is going to be all zeros. Yeah, block size. This given block size of 4 byte. Byte meaning 8 bits. 8 times 4, 32 bits. So you will be given the block size. It's not going to be always 32. Yeah? So if there's something in the data, okay, we brought from the main memory into cache, they're automatically 0 to 1. Okay? And if that data is the one that I want, then it's going to be hit. If it's not one that I need, then I need to go down and bring it here, replace that. Still, valid bit is 1, but in that case, it's a miss. So let's do this. Find the total bits required for cache if direct map cache with 1 kiloword, and then block size of 4 bytes, and then 32-bit addresses. And we're using byte addressing. So the first thing, we need to do the 2 to the n equals to cache size over block size. What's the cache size? 1K word, block size 4 bytes, and then word we want to change it to byte, which is 4 byte. 4 by 4 byte cancel, 2 to the power of 10. Therefore, n equals to 10. Now we need to find the text size. Text size 32 minus n. We found that n equals to 10. N plus m plus 2. The block size is given 4 byte. That is 1 word. Therefore, it's a 2 to the power of 0. M equals to 0. So now text size is 32 minus 10. We have n equals to 10. M equals to 0 plus 2 equals to 20. The valid bit is 1. So finally, the total size 2 to the n times block size plus text size and the valid bit. So it's a 2 to the 10 plus 4 times 8 plus 20 plus 1. Has to be all in bits. So that's why we have 4 times 8, 4 bytes of the block size, 4 times 8 plus 20 plus 1, 53 kilobits. So this is the 2 to the power of 10 valid bit, 20 bits for the tag, and in the data, 32 bit, but we have a 4 bytes. So that's why we need to have offset for 2 bits. So this is 00, 01, 10, 11. Next, how many total kilobits are required for direct map cache with the 16 kilobyte of data and 4 word blocks, assuming a 32-bit address using byte addressing? Show the partition of memory address. Okay, so let's do that. So now we have the first one is 2 to the n equals to cache size over block size. What's the cache size? 16 KB, and then block size 4 word block. So 16 KB over 4 word. Word is 4B. So 16B cancel, 2 to the power of 10 again, n equals to 10. And then text size equals to 32 minus n plus m plus 2, and then To figure it out, value of M, we're going to look at the block size. Block size is 4 word, therefore it's a 2 to the power of 2. Now M equals to 2. So 32 minus 10 plus 2 plus 2, and that'll give us 18. And then value bit is 1, therefore 2 to the 10, 4 times 32 because 4 words. And then 18 plus 1, 4 times 32 is 128, 147 kilobits. That's the answer. Yeah, so that's the part B. So we need to put tag, index, offset. To remember this order, tag, index, offset. Offset is always the lower bit. So we need to figure it out, index bits first, and then offset bits, and then 32 minus those two is gonna be tag. M plus 2, that'll give us offset, right? And when we look at this, it's much wider. So we have 1 word, 2 word, 3 word, 4 words. And each word we have a 4 bytes. Therefore, we need to have offset of 4 because now we have total 16 bytes. In order to name those 16 bytes, we need to have 4 binary bits to name them all. Yeah, the whole diagram. The block size is the 4 word. So block size is the whole thing as a block, this whole data. So the 4 word, 1 word, 2 word, 3 word, and 4 word. Each word is a 32 bit. And each word we have a 4 bytes. So there are total 16 bytes in a block. We okay so far? And then we want to name these 16 different bytes using binary numbers. Then we need to have a 4 bit 0000 all the way down to 1111, which is 15. So the offset value is 4. So just verifying how we calculate this. And then n, 2 to the n, is 10, 2 to the 10, the 1024 blocks. So the cache size is height times width. How you find the width? Valid bit, tag size, block size. So this is height times width. That is this. Now since I ask you to find in kilobits, I'm going to keep this 2 to the power of 10 as a kilo, and the rest you add them up, 147. Yeah, tag values, it depends on the offset plus the index. So always we're going to use 32-bit as a total length of memory address. So 32 minus the index plus offset. This is assembly code, go through here, and then we're calling an LDR and bring it 4, 12, 8, and into here. So this is, what happened. And miss rate 3/15 because we're going to do 5 times 3, so 15, right? Because this is loop. So that's the miss rate calculation. Valid bit is 0 as an initial because cache is empty. And whenever we put 1 into the cache, now it's going to change to 1. Okay. So the first 4, okay, since there is a byte addressing in the cache, lower 2-bit is going to be offset, right? And then index value is going to be 001, right? Where is 001? Right here. And when you bring the content, I just need only byte 4. However, in the cache, we bring as a whole block. Even though I just want to call 4 as a byte address or only 4, we need to bring everything. Now, how do we know where is 4? 4 is the offset as a 00. So the first one is 4. Offset is a 01, it's going to be 5. Offset is 10, it's going to be 6. Offset of 11 is going to be 7. So always when we bring from main memory to cache, we bring them all as a block, whole block. If this is 1 word, there's going to be 4 of these, okay, 4 bytes. If this was 2 words, then we need to bring all 8 bytes as a one shot. So always bring the content as a block. Make sense? So this is the content of the cache in here. put memory address into binary number, and then depends on the description, it's only one word block. You need to partition this data into 4 and bring the 4, and you need to bring buddies. And byte address 12 is 00001100, and offset is 00, and the location of the index is 011, and my tag value is 00012. Bring my buddies 12, 13, 14, 15. And then 8, I put it into binary number. Lower 2 bit is the offset. The middle 3 bits, 0, 1, 0. And my tag is going to be 000. And 8 plus my buddies, 9, 10, 11. Bring them all. And since we have 4, 12, 8, after that, it's going to be just hit and hit and hit.